Now, in this video, we're going to take up one more problem on the overhanging beam. Draw the SFD and BMD for the beam shown in the figure, marking the values at salient points. Locate the point of counterflexure and of point of maximum bending moment. Determine the values of maximum bending moment. So, this is the figure which is having a overhanging beam. So, we have a support at A and D, and we have a point load of 20 kilonewton at B and 15 kilonewton at point C, and 10 kilonewton at the point E. At point E is 1 meters from D, and then point B is 2.5 meters from A, and point C is 4 meters from A. And we have a vertical reaction which is acting upwards at the point D, which is 5 meters from A. So now, first we need to find out the support reactions. So to find out the support reactions, taking the moments about the point A, the clockwise couple will be equal to anti-clockwise. So clockwise moment will be equal to anti-clockwise moment. So taking the moments about the point A, that is RdV into phi, will be equal to 20 into 2.5, then 15 into 4 plus 10 into 6. On simplification, you will going to get RdV will be equal to 34 kilonewton. Also, we know that the sum of the vertical reaction which is acting upwards should be equal to the sum of the vertical reactions acting downwards. So RAV plus RdV will be equal to 20 plus 15 plus 10. So on simplification, RAV will be equal to 45 minus 34. Therefore, RAV will be equal to 11 kilonewton. So RAV will be 11 kilonewton, RdV will be equal to 34 kilonewton. So once you get this, now we go for the analyzing from individually. So first we will going to consider a vertical reaction or the support reaction at the point A, and also at the point B we have 20 kilonewton acting downwards. So for a span of 2.5 meters. So when you're considering the shear force at the point A, since it is the load acting upwards, so it becomes positive. So it will be plus 11 kilonewton. Between A and B, as there is no other load acting at the between A and B, it remains constant at plus 11 kilonewton. So SF at the point B, we have 20 kilonewton acting downward from the point B. So that will be plus 11 kilonewton minus 20, which will be equal to minus 9 kilonewton. So the shear force will going to change its sign from the positive to negative at the point B, because due to the point load, it drops down from 11 kilonewton to minus 9 kilonewton at this point. So what will going to be the bending moment at the point A? Bm at A will be equal to 0, and the Bm at the point B will be equal to plus 11 into 2.5, which will be equal to plus 27.5 kilonewton meters. So from here to here, from 0 to plus 27.5 kilonewton meter, you're going to draw a linear line between these two. It's a straight line. Now, we will consider again between B and C and the point load at the point C now, acting downwards. So between B and C, what happens, as there is no other load which is acting, so it is going to remain constant at minus 9 kilonewton. Then at the point C, SF at C, minus 9 minus 15, it becomes minus 24 kilonewton. So that is from minus 9, it drops down to 24 kilonewton due to the point load at the point C, which is 15 kilonewton. So the bending moment at the point C now, once you consider the bending moment at the point C, see what happens. You're going to get from plus 11 into 4, plus 11 into 4, minus 20 into 1.5, which will be equal to 14 kilonewton meter. So from 27.5 kilonewton meter, it drops down to 14 kilonewton meter at the point C for the bending moment diagram. So we have considered from A, B, and C. Now we are going to go further from C to D, and then at the vertical reaction at the point D now. So we have from C to D, and also the vertical reaction acting upwards at RdV is equal to 34 kilonewton. So as we go from shear force diagram between C and D, what happens? It remains constant as there is no other load acting between C and D. So it remains constant at minus 24 kilonewton. So at the point D, which is acting upwards by plus 34 kilonewton. So therefore, SF at D will be equal to minus 24 plus 34, which will going to be plus 10 kilonewton, which is going to the positive value. So here at the point D, because due to the point load which is acting upwards, the SF will going to rises from it increases from minus 24 to plus 10 kilonewton because due to the point load which is acting upwards at the point D by 34 kilonewton. So what will going to be the bending moment at the point D now? So it is plus 11 into 5 plus 11 into 5 minus 20 into 2.5 minus 15 into 1. On simplification, you will going to get it as minus 10 kilonewton meter. So now at the point D, bending moment drops down from plus 14 kilonewton meter to minus 10 kilonewton meter at the point D. So the bending moment is changing its sign from positive to negative at this point. Then we will going to consider the point E now, between D and E and also at the point E, that point load. So once you are considering that, so here between D and E, as there is no other load acting between D and E, it remains constant at plus 10 kilonewton. So the bending moment at the point E will be equal to what happens to the bending moment at the point E. So bending moment at the point E will be equal to 11 into 6 minus 20 into 3.5 minus 15 into 2 plus 34 into 1 will be equal to 0. So here, so BM at E will be equal to from minus 10 kilonewton, which is dropped down to bending moment at the point Z, it will be equal to 0. So it becomes 0 here. So what will going to be the maximum bending moment? We will going to change. So the maximum bending moment will going to occur where the SF is changing its sign. So when you see here in the shear force diagram, you can see the bending moment is changing its sign from positive to negative once, and also from negative to positive once. Between D and E, what happens in the shear force? It is there is no other load is acting between these two, so it remains constant at 10 kilonewton. So that is what you're going to get from here to here, which is going to be plus 10 kilonewton. So that is what we have shown. It is constant at plus 10 kilonewton. This is the shear force. Now, once you are trying to find out the maximum bending moment, so when you are considering that, maximum bending moment will occur where the SF changes its sign. SF is changing its sign at B and D now. So once you do that, hence the bending moment is maximum at these 2 points. So we have a positive bending moment maximum at this point B, which is plus 27.5 kilonewton meter. Then you have at this point again the bending moment changing its sign from negative to positive. So you are going to get the maximum negative bending moment. So maximum negative bending moment is at the point D, which will be equal to minus 10 kilonewton meter. So, but as the bending moment changing its sign from positive to negative, so we have the point of contraflexion. So we have the point of contraflexion. So we need to find out where the bending moment changing its sign from positive to negative, at what distance it is changing its sign from positive to negative. So we will going to consider that distance as x from the point F towards E. So let F be the point at a distance of x meters from E where the bending moment changing its sign. So what is the bending moment at the point F now? So the bending moment at the point F, definitely we know that the value is changing from positive to negative. So obviously it should be 0. So that is equal to 0. So then it will be minus 10 into x plus 34 into x minus 1. So once you expand, it is minus 10 into x plus 34 into x minus 34 will be equal to 0. So 24 into x will be equal to 34. So on simplification, x will be equal to 1.1417 meters from E. So the point of contraflexion is at 1.427. So it is 1.417 meters from E. It is not. So that is how you will going to get 1.427 meters from E. So that is the distance where it will going to get 1.427 meters from E, which is F. So this is how you will be able to analyze the shear force diagram and the bending moment diagram and get the final solution. Thank you.